So section 5-2 deals solely with right triangles. We have 4 theorems associated with right triangles. All of them in some way mirror the theorems and postulates from chapter 4. So the first theorem is 5-5. It is lovingly referred to as LL. If you think about the parts of a right triangle, what would LL be referring to? Leg, leg. We are proving triangles congruent. 2 right triangles congruent. All right triangles have what in common? Right angles. So what you're going to find in right triangle congruence theorems is that we don't have to mention that right angle. Because in chapter 4, didn't you have to have 3 corresponding parts congruent to prove a triangle congruent? It had to be the right 3. And there are 4 theorems for that. SSS, SAS, ASA, and AAS. What was the one that you couldn't have? SSA, which spells a bad word backwards, right? Okay. One of those we're not going to have, and one of them will be a little surprise. So notice that I only have 2 things here instead of 3. With right triangles, you only have to prove 2 things congruent because all right triangles have a congruent right angle, and that's a given. It's like a no duh. It's like me telling you you have to have air to breathe in order to survive. Do I really need to tell you that? Don't you know that already? You should. All right, so LL says, if the legs, write this down, of one right triangle are congruent to the legs of another right triangle, then the 2 triangles are congruent. Here's why. Let's do. Alright, so I would draw these pictures somewhere tiny off to the side, but I'm going to draw them big for you. So here's your 2 right triangles. It says that somehow you're able to prove the legs congruent, the corresponding legs. So would that be these and these? In chapter 4, what theorem would this have been? So you're saying that the angle is included. Is that correct? Yes. It's the angle that's created by those 2 sides. So in chapter 4, this would have been SAS. But if we are proving right triangles congruent, you can no longer say SAS. You have to say, in this case, LL. Because you're not going to prove an angle congruent, because it's already a no duh. So you can't use SAS because in your proof, you're not saying that the 90-degree angle is congruent. So therefore, you can't use SAS, you're using LL. So if you're going to shorten your proof, you have to use the right theorem. Does that make sense? Pardon? Leg, leg. LL is leg, leg. Okay? All right, next one. Theorem 5-6. Theorem 5-6 is lovingly, it's kind of a funny one. It's lovingly referred to as ha, 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 ha. Ha, 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 ha. It's a funny one, right? It's a joke. All right. What does H mean? What do you think A means?
Angle.
Which angle?
The right angle.
This A will never ever refer to the right angle, because what did I say about the right angles in a triangle? We already know they're already congruent, so we don't have to mention it. So aren't there 2 other angles in a right triangle? What kind of angles are they?
It's the hypotenuse.
They're acute angles, right? So this A will always be referring to one of the two acute angles in the right triangle, never the right angle. So it is the hypotenuse and an acute angle. So if the hypotenuse and an acute angle of one right triangle are congruent to the hypotenuse and acute angle of another right triangle, then, oops, I'm running out of room there, the two triangles are congruent. Here's the reason why. First triangle, second triangle. So this one says hypotenuse. How do I know where the hypotenuse is? It's the longest side, which is across from the right angle. So that must always be the hypotenuse. And it says either one of the acute angles. So let's say we chose this one. From chapter 4, what theorem would this have been? So you're saying the side is not included, is that correct? Yeah, the side's not included because if it were, it would be in between here, and that's not the side we're looking at. So this side is not in between those two, so it would have been AS. Well, what if we hadn't chosen this angle and instead we had chosen this one? Would it still be AAS? Yes. So whichever set of corresponding acute angles you choose, you would have had AAS. But now, you're not going to use AAS, you have to use ha. Ha. Aha. Next. Same thing, because you're going to mark up your triangles and you're going to say, do I have a hypotenuse and an angle? Do I have a leg and a leg? Or, we got two more. So it's the same thing that you did before. But I just want you to see that they're really the same theorems that we used in chapter 4, except for one of them. But we're shortening it up. So theorem 5.7 is lovingly referred to as la, a note to follow so. Just keeping you awake. So what does that refer to? Leg and angle. Which angle? An acute angle. So this one says if one leg and an acute angle of one right triangle are congruent to the corresponding leg and acute angle of another right triangle, then the triangles are congruent. Again, let's see which theorem that pertains to. So draw your right triangles. So let's say that we choose these legs. You could have chosen these, one of them. And let's say this angle here. In chapter 4, what would that have been? So you're saying the sides included. Is that correct? Sides in the middle? Yep. So this would have been ASA. Would it be different if I had chosen instead the other angle? That's still ASA? Is that side included? No. What would this have been? AAS. So this one, you would have had one of the two, depending upon which leg and angle you chose. Now, is that going to change if I choose the other leg? What's that one? It's still ASA, but what if I chose the other angle combination this time? AS. So this would have been one of those two. But now that it's a right triangle, you have to call it law. Last one. There were 4 in chapter 4, there's 4 in chapter 5. All right, the fourth one. Now ponder the fourth one for a minute. Which one have we not had from chapter 4 yet? Nope, we had AS. Side, side, side. How can we have side, side, side if always the right angle is technically part of it? You're not going to have side, 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 are you? We can never have angle, 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 because remember that can be a dilation, bigger or smaller. So look at what happens with this one. What's the one combination we haven't had so far? HL, right? So this one happens to be a postulate only because postulates are non-proven theorems. It's not that they didn't feel like proving it. Well, it's not that it can't be proven. They didn't feel like proving it. Put it that way. We could put it in a theorem, but they just didn't. I think they got tired. But this is lovingly referred to as HL. H meaning hypotenuse, L, leg. So it says if the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and corresponding leg of another right triangle. Oops, got excited there. Then the triangles are congruent. This is an interesting one. Let's see which one this is. I'm going to move that up a smidge. So here's your triangles. Assuming they're congruent, right? So our hypotenuse are congruent, hypoteni. It's plural. And just choose one of the legs, but make sure they're corresponding. So let's choose that one. What would this have been in chapter 4? ASS, or I prefer to write SSA. Was that allowed in chapter 4? No. It is in this time. And I'll prove to you why in a minute. Would it have mattered if I would have chosen that set of legs? Would it still be SSA? Yes, because the angle, the right angle, is not included. So why is it that we can use the bad word spelled backwards, only it's really not, because we'll be using HL, which doesn't spell a bad word, so it makes me feel better. Look at what happens. If this has to remain a constant, assuming I drew a straight line, a constant measurement, right? I can't change the length of that hypotenuse, agreed? And I can't change the length of that side, so we're going to keep that stationary. That means that this leg right here could get larger or smaller. But that has to remain a right angle. So look what happens if I make this angle here bigger, because that doesn't have to remain whatever it is now. So if I make it bigger by keeping the same length, what has to happen to this side? It has to go in, doesn't it? Which does what to the right angle? Changes it. That can't happen because that has to be right. So there's no other angle that this could be other than that for that to be a right angle. Same thing if I made it smaller. Let's say that I made it smaller. What would happen to this side? It'd have to go out, which changes the fact that that's a right angle, which we can't have. So does it make sense that this third side could only be a set length? Okay, so in this case with right triangles, SSA is allowed, but we're going to call it HL. So those are the four, and they kind of are catchy if you learn them as ha, la, HL, and LL. Ha, la, HL, and LL. Learn them, know them, and love them. All right, so let's do some examples. Example 1. And then we're going to do 2 proofs after this. I'm so psyched, I cannot tell you. If you get your brain thinking, maybe we'll warm up in here. All right, you are going to find the values of x and y so that triangle JKL is congruent to triangle MLK. So you need a picture and some other information. So here's J. Well, what do you know about these triangles to begin with, just looking at the congruent statement? More than the fact that J is congruent to L. I'm sorry, M. What else do you know?
They share L.
They share L and? Okay, so what does that mean? What do you want, Stephanie? Take no more than $5. All right, so they share a side KL, don't they? Just looking at that statement. Now, is K congruent to K over here? No. So look at the picture. Right here is L, and this is K. So there's one triangle. Anything for my daughter. I love you, Stephanie. All right, there's a right triangle. Angle L in that triangle is right. And then down here would be M. And in that triangle, angle K is the right angle. Which makes sense why K and L are congruent. They're both right. Other information that you need to know. Angle J right here is equal to the expression 3 minus 10x in parentheses to the 0 degree. So that's the angle measure. And then this angle right here, which is the small angle K, which is different than this one, is equal to 8y degrees. And this little angle here, L, is equal to 10 y minus 8 degrees. And M right here is equal to 2x minus 15 degrees. You have to use some knowledge about right triangles. What do you know about these two acute angles in a right triangle? They don't equal each other, not necessarily. They add to 90 degrees. So you could say this plus this is equal to 90 degrees. What's the problem going to be with that? You have two variables. Does that happen here too? Yes. In this particular case, I would avoid that, if at all possible, because you'll end up, and we have two equations with two unknowns, so couldn't we solve that as a system of equations? Okay. When you do your system of equations, you've got to line up your x's and y's on the left, lining the x's under each other and the y's under each other, and the constants, which are the numbers without the variables, on the right-hand side of the equal sign. Then you're going to have to multiply one equation or both by different numbers to get either the x terms or the y terms to cancel out, so that you can just solve that equation for the one variable. Once you get one variable, can't you plug it back into the original to get the second variable? That's your review of systems of equations from algebra that you are to master. Now I'm going to try to avoid that on here. You might not be able to avoid that on your homework tonight. So if you need more help with systems of equations, see me at lunch in room C206 today, right after this class, or tomorrow morning before school. However, don't we also know from the congruent statement that J is congruent to M? So this angle right here is congruent to this angle right here, and that L is congruent to K. So this angle here is congruent to that angle there. So my suggestion would be that you set corresponding congruent angles equal to each other. And you will have a pleasant surprise in this case, because look at what we have. If I set these two equal to each other, the J and the M, don't I end up with 3 minus 10x is exactly equal to 2x minus 15? Right? And if I set the L and the K over here equal to each other, I will have 10y minus 8 is equal to 8y. That way, each equation only has one variable. That would be the easier one, or the easier choice to solve. So you go ahead and do the math. Do the algebra right now. Show the person sitting next to you or around you what your answer is when you're done. Show proper algebra, not scratch algebra or lazy algebra. I want to see what you're doing to both sides. What kind of answers do I want? I don't want decimals, I want fractions. That's a little bit of a hint. Fully reduced. Please share your answer with the person sitting next to you or around you. Okay, what did you get for x? 3 over 2. Reduce that fraction. You should have had 18/12. Reduces to 3 over 2. And then what'd you get for y? 4. Here's my work. If your work doesn't look like mine, it's wrong. What's wrong? No, just leave it improper. Because if we were to use that in a different equation, you'd want it improper. Yeah. Don't turn it into a decimal under no certain circumstances. Okay. You okay with that? You ready for some proofs? Not really, but you actually like these proofs because they're going to make sense to you today. Austin? Nope. That's what your time before class is for. This is important. All right, you ready? Can I flip it? Okay, here we go. When you do your proofs tonight, you absolutely cannot do lazy proofs like I've been seeing. I have to see the given. I have to see the proof statement, and I have to see the picture, along with both your statements and your reasons. You've got to do the whole thing. So, this particular one actually has a word problem associated with it, but I'm not going to make you write it down. So, example 2. Here's your given. I want you thinking what you can conclude from this given. Segment BD is a perpendicular bisector of triangle ABC. So isn't that something from yesterday? Right? what do you know about perpendicular bisectors? They bisect the opposite side into two equal segments. So that's one thing we're going to be able to conclude, which probably means we have legs or hypotenuse congruent on my right triangles, which we're going to have right triangles because that's the section that we're in. Isn't there a second thing I can conclude from a perpendicular bisector? Not that they have right angles. The definition of a perpendicular bisector says that the bisector is perpendicular to the opposite side. So the thing I can conclude about a perpendicular bisector is that it's perpendicular to another segment. Then what can we conclude from the perpendicular segments, Amanda? That we have right angles. So we have to go 2 steps to get to the right angles. You cannot jump from perpendicular bisector to having right angles, because right angles are not in the definition of a perpendicular bisector. Do you see why? Okay. So those are the 2 things. So we're going to end up getting a right angle out of that. And the reason why it's important that we identify that eventually we're going to prove we have a right angle, if we're going to use any 4 of those theorems that we just went over, you have to prove first or state first that your triangles are right. Is there anything in here that says that you have right triangles? So you cannot assume that until you state it. Once you state you have right triangles properly, then you can use any of those 4 theorems, Ha, La, HL, or LL. And here's what we're going to prove. Your job is to prove that triangle ABD is congruent to triangle CBD. Here's your picture. Here's A and B. Here's C. And so this is the big triangle ABC. And this says that BD is a perpendicular bisector. Well, B is one of the vertices of the triangle. So that means that my perpendicular bisector must actually go through that vertex, which it doesn't have to. But it has to be perpendicular to this. Oops. So this point right here is D. And that picture will be given to you just like that. And you've got statements and reasons. You're going to find that these proofs are long, but easier to do. You're going to combine knowledge from 5-1 and today to prove the triangle is congruent. Get used to marking up your picture. So again, the fact that BD is a perpendicular bisector, what 2 things were we able to conclude? Again. Well, we're going to conclude that BD is perpendicular to AC. From the fact that these 2 are perpendicular, we are going to conclude in a second statement that we have right angles here, right? Because perpendicular lines form what? Right angles. So it's going to take us 3 steps to get to that. Are given, to the fact that these lines are perpendicular, to the fact that we have right angles. Okay? From the minute I have right angles, can't I say that these are now right triangles, these 2? Once I say that I have a right triangle, I'm going to use Ha, La, HL, or LL. So let's see which one it is. The other thing that we could conclude from the fact that this is a bisector was that DC was congruent to AD, because it splits that into 2 equal pieces. Is this a leg or a hypotenuse? A leg. Isn't it a leg? The hypotenuse is always across from the 90 degree. So make sure that you know which is which. So I've been given a leg in that given. That's one of the 2 things I need to prove these 2 smaller triangles are congruent. What's the other thing we can definitely prove is congruent? Don't they share a side? So we can definitely prove that DB is congruent to itself. Why? No, I heard it. Yeah, if the same thing is congruent to the same thing, isn't that the reflexive property of congruent segments? Okay, and is this a leg or a hypotenuse? A leg. So aren't we going to use LL to prove those 2 triangles congruent? Here we go. We only have one given, so start with that. Segment BD is a perpendicular bisector of triangle ABC. Why? Given. One of the things you have to learn in this section is that we have to state the triangles are right first. So to get there, I need to claim we have a right angle because that's in the definition of a right triangle. Perpendicular bisectors do not claim we have right angles. It claims we have what? Not yet. We can't use congruent segments to prove a right triangle. What? What'd I say? So one thing was that we had two congruent segments. What was the other thing that a perpendicular bisector does? Perpendicular bisector. Two segments are perpendicular. So isn't segment DB perpendicular to segment AC? Why? How do we know from here, from this statement here, that this is true? Definition of perpendicular bisector. You have to have all that. You just say definition of perpendicular, I think you're talking about lines. If you just say definition of bisector, it could be an angle bisector. So you have to have both. Then what did we conclude from perpendicular lines? They form right angles. So the angles that are formed would be angle CDB and angle ADB are right angles. Why? From here to here, why? From here to here. What's this? There you go. Definition of perpendicular lines. In the definition of perpendicular lines, it says that they form right angles. The minute I know I have right angles, what can I now state? We're trying to prove triangles congruent. Before I can use LL, what do I have to state? The triangles are right. Right. So I can conclude from having right angles in a triangle that those triangles are right. So triangle CDB, I actually should use what they have here. So let's say triangle ABD and triangle CBD are right triangles. How do I know that? From the fact that I have right angles, that they are right triangles, what tells me that? Definition of a right triangle. So we have a lot of definition usage here, right? I'm going to move that up. Now, here's the deal. You need to learn this progression. Step 2 through 4 always have to go together in that order. If your given has not told you that you have right triangles, you absolutely, positively have to put these three things together. If you're given perpendicular lines, you have to conclude you have right angles. Once you conclude, put that cell phone away. Once you conclude you have right angles, then you can conclude you have right triangles. Those three have to go together. Okay? Now I can start using my right triangle congruence theorems. So we want to do LL. What should I start with? Well, here's the deal. Since we already started with this in our given, wouldn't it make sense to mention AD and DC first? Yes, it would. All right, so I'm going to mention the fact that segment AD is congruent to segment DC. Why? Right, the definition of the perpendicular bisector, again, remember it told us two things. So we use it again. Definition of perpendicular bisector. There's two parts to that definition. We use both of them. Sometimes you don't. So isn't that my first L? I have one out of the two. Now how do I get the second L? Right, segment DB is congruent to segment DB. Same thing equals the same thing. Reflexive property, you have to keep going, of congruent segments, because it could be congruent angles. Now that we've mentioned our second L, what can I say? Yeah, I've proven the triangle's congruent, haven't I? So number 7 is our prove statement, and you have to write exactly as it says. Triangle ABD is congruent to triangle CBD. Why? LL. The reason for the congruence triangle statement has to be ha, la, HL, or LL. So that one's done. Did that make more sense than chapter 4?
Yes.
Okay. No, it should be. It should. It shouldn't have created too much stress on your brain. The one thing that's new is what? What's the one thing that's different? This progression right here. Write yourself a note. Learn it. Study it. This is the new progression. Perpendicular to right angles to right triangle. All right, let's look at the second theorem or proof. All right. Example 3. Pardon? You'll find it easier. Here's what you've been given. You're given a lot in this one. Segment PR is perpendicular to segment QR. What do we conclude from perpendicular lines? That we have a right angle. Okay? What do we conclude from a right angle? That we have a right triangle in today's, right? Okay, so your other one is going to be segment PS is perpendicular to segment QS. Won't we have that same thought progression? Perpendicular to right angle to right triangle. We're going to end up with 2 right triangles, which means we'll have ha, la, HL, or LL. And then they also give you segment QR is congruent to segment QS. Don't you think that that's going to be a leg or a hypotenuse? Okay, here's what you're proving. You are to prove that segment QP bisects angle SQR. So what are we trying to prove that QP is? If it bisects an angle. Right. What's the characteristics of an angle bisector? What's the definition say? It goes from a vertex and splits an angle into 2 equal angles. So in order to prove this, don't I have to somewhere prove that I have 2 equal angles? Before I can prove 2 angles are congruent, it might be handy to prove that triangles are congruent, because aren't angles parts of a triangle? And aren't corresponding parts of congruent triangles congruent? We had that in chapter 4. How exciting it's coming back. So here's Q. And then P is right here. I want you to draw a ray from Q through P. And then S is here. I want you to draw another ray from Q through S. And R is here. Draw another ray from Q through R. And then connect R to P and P to S. And then you're going to have statements and reasons. What did I say you need to get used to doing? Marking up your picture, right? So let's start with PR is perpendicular to QR. What did we conclude from perpendicular lines? Won't there be a right angle there at R? And then PS is perpendicular to QS. Again, won't we have a right angle here? These 2 parts of the given, we conclude the same thing, that we have right angles. Wouldn't it make sense to split the given with these 2 being in one and that being by itself? Okay, so you're going to see me doing that. So immediately, once I do that, because notice if I'm trying to prove that QP bisects this angle here, I'm going to prove those angles are congruent. But nothing here tells me that. All I have is that QR is congruent to QS. That's one part of my right triangle. What's the other part I can prove definitely? QP is congruent to itself, right? So is that ha, la, HL, or LL? What is this? My hypotenuse. How do I know that? It's across from the right angle. And isn't this a leg? So isn't it HL this time? HL. I'm going to have to prove these right triangles congruent by HL. Also noting that I have to state I have a right triangle before I can prove that. Once I prove these are congruent, aren't any of the corresponding parts congruent? If I can prove those two angles congruent, doesn't that prove that that bisected it? Here we go. All right. Let's start with the first part of the given. Segment PR is perpendicular to segment QR. Also, segment PS is perpendicular to segment QS. Why? Given. From perpendicular lines, what do we conclude? That we have right angles. So name those angles properly. Angle Q, S, P, and angle Q, RP are right angles. Why? Definition of, this isn't a perpendicular bisector. What are these? Perpendicular lines. Because perpendicular bisector wasn't mentioned this time, our reason can't be perpendicular bisector. So it has to be perpendicular lines. So pay attention to what you're concluding from. All right, then from right angles, what do we conclude? So triangle QSP and triangle QRP are right triangles. Why? Definition of right triangles, because the definition of a right triangle says you need one right angle. Didn't we just state that they have a right angle? Okay. Now that I've mentioned I have right triangles, can't I now progress with HL? All right. H comes first, although it doesn't matter whether you do HL or LH. So because H comes first, and that's how I've been teaching you, we can jump to the QP equals QP because that's the hypotenuse. So, statement 4, segment QP is congruent to itself. Why? Reflexive property of congruent segments. Isn't that our H? Bless you. We need just one more L before we can state triangles congruent. You okay, Dan? Squinting? All right, so then how do we state our leg congruence? Isn't it part of our given up there? So let's bring down the third part of the given. QR is congruent to QS. Why? Given. And that's our L. So once we hit those two parts, what always follows? Not the prove, because that's not what we're proving. But before we can prove that, we have to state the triangles are congruent, right? So triangle QSP is now congruent to triangle QRP. Why? HL. Now, I'm going to drop this down for a minute. So if the triangles are congruent, wouldn't you agree that these angles right here are corresponding and congruent? Don't we know that corresponding parts of congruent triangles are congruent? So I can state that this angle, SQP, and this angle, RQP, are congruent. That's my next conclusion. Angle SQP is congruent to angle RQP. That's not a K, it's really an angle marker. Why? CP-CTC. Notice that CP-CTC always follows the triangle congruence theorem. This time, however, it is not the last thing in our proof. Once I state that those two angles are congruent, right here, what can you conclude about QP? By what? By the definition of an angle bisector, right? Angle definition says that it cuts an angle into two equal pieces. Haven't we done that? So our last statement is the proof. Segment QP bisects angle SQR because of the definition of an angle bisector. And yes, you have to write all that. Now, was that such a hard proof? It's long, I'll give you that. But you understand the progression this time, don't you? It's much easier than when we did chapter 4. So my suggestion would be that you go back to last night's homework, relook at some of those things, and come visit me for help, and then tomorrow I'm answering all questions.